So our next speaker is Dr. Wim Audenaert. So Wim holds a PhD and Master of Science degree in Environmental Engineering, and he's also co-founder and CEO at AMT. So AMT is the company that helps utility consultants and technology developers reducing and omitting on-site the piloting efficiency, obtaining optimal process design operation. So their key solutions include a unique CFD combined with kinetic model for biological and chemical treatment processes. So, so I think I'll leave the time to Wim talk about their CFD combined with kinetic model to reduce the N2O emissions.
Thank you very much, Leo, for the introduction. So yeah, hi everyone, I'm Wim Audenaert. Pleasure to be here in this webinar. Thanks for Mia setting it up, and thanks for the participants of being here. I think this presentation nicely connects to the story Mathieu just said. And I especially like the last comment on his last slide, which was, it is quite challenging to account for the heterogeneities in a reactor. So there are quite some gradients. So it nicely connects because thanks for introducing all the kinetics, Mathieu. And I will now build further on that, looking in 3D. So we will bring in the spatial components. Yeah. So this presentation was put together in collaboration with my whole team and of course all the customers we currently work with. So when we look at N2O emission, in fact, it is quite a complex process. I think everybody understands this. Not only conducting measurement campaigns or getting them right is complex, but actually how everything works behind the scenes within a bioreactor is quite a challenge. So the first step is actually the production. Just imagine we would have no biological production of N2O. We would have actually no greenhouse gas emissions from N2O. So this is really where it all starts. It gets produced, and we already saw a couple of speakers introducing the pathways. There are actually three main pathways, one by the heterotrophs, yeah, and then two pathways, the hydroxylamine and the other pathway by the autotrophs. So these are the nitrifiers. So yeah, these bacteria are actually the root cause. They are doing certain things well because they help us treating wastewater, but unfortunately, they also produce N2O. And then, of course, once your N2O gets produced in the liquid phase, it gets transported in your bioreactor through the water flow. Yeah, so that is really the transport and diffusion of your N2O, and in the end, it gets emitted, and that is really causing the greenhouse gas emissions. Yeah, so this is really the three very different steps, and the complexity a bit with measurements is that what you measure is related to steps 2 and 3. So if you do gas measurements, you actually directly measure the emissions in a certain zone. But as you can see on this CFD image, it can be quite heterogeneous, difficult word, sorry, in a bioreactor. So it can be quite some variation on data. Yeah. And if your influence changes, these zones can also shift. Same here with liquids. If you look at it, yeah, it can be quite a change happening in your system caused by local dissolved oxygen, local ammonia being somewhere. So actually what we measure is the result of the root cause. Yeah. So in the end, what has a climate impact is of course the emissions. So you can actually treat the gas as well. Some utilities are looking into this, but really to solve the issue, probably we have to really look at the root causes. And this is really the biological kinetics locally somewhere in your bioreactor. So this is a webinar on modeling, and I tried to summarize a bit the benefits of models in the N2O question here at the challenge. Well, utilities are mainly in the assessment stage right now. Many of them want to quantify their emissions, and models can be used to help quantifying the emissions in a dynamic context. They can also help you comparing different plants or prioritize them. And of course, they can also enhance, reduce, or replace on-site measurements. Because this is really, the question is this really feasible for many utilities to go that deep in measurements? Then, of course, we have the mitigation stage, and we saw a couple of examples already. You can virtually test mitigation strategies. Then you can do a comparative analysis. And then you can also try to optimize the effluent quality. Because we should not forget, for example, in Europe, we will have very stringent effluent limits coming. with the new framework directive, and especially 2027 is a key moment. So utilities might want to mitigate N2O, but only under the condition that they don't lose or even improve effluent quality. And this is really, really a challenge that should not be underestimated. In the end, models probably can also help to really develop the generic learnings every utility can apply, because this is currently a bit lacking. So when you look at the tool we have been developing, it is a combination of a CFD model, which is a computational fluid dynamics model. It's a 3D simulation of the flow in a bioreactor. And we combine it with the biokinetics. So it has a physical part in it. So this means the transport of your N2O, the fusion stripping, it's all included there. And then, of course, it has the biological part in it, which are the different pathways of N2O. And the core of the biological model is really the ASM models, the activated sludge models, which we have heard about in this webinar before. So in the end, you get plots like these top views or 3D views of your local N2O or local dissolved oxygen and things like that, yeah, in the gas and the liquid stage. So when we look at some case examples, how do you now apply this and how do we use that now in certain projects? Well, this is the first case in New Zealand in collaboration with Watercare. Well, they have a specific pilot over there next to their full-scale plant to really get more understanding on N2O, because their goal is really to mitigate it and to mitigate through process understanding. So you can see you have a very simple setup here, an anoxic zone, return activated sludge inlet coming in. So high COD, of course, here, high ammonia, it's all coming in. And then here you have your aeration. So your flow goes like this and then goes to the aeration. And they are typically measuring with some sensors, either gas hoods or liquid measurements. So if you simulate that with that combined model, you can actually visualize your liquid N2O concentration. For example, you can see it's way higher in the anoxic zone in this case compared to the aerobic zone. But you can also see, if you look at the gas, that's a bit the opposite, because the stripping really, really happens in this case, mainly in the aerobic zone. So if you would measure with a hood, you would measure, of course, your N2O here. If you would measure with a hood here, you would measure some emission, but especially the liquid measurements would be higher in the anoxic zone. Yeah, but this is just a very simple case example illustrating what happens. But what these measurements would not tell us is what is really the root cause? What is causing the N2O production in this case? And that's why we look one level deeper now. So we are looking from the side now in this reactor. So this is a side view. Yeah, you see the anoxic compartment here and the aerobic zone here. And what we visualize right now is not the concentrations of N2O, but the production rate. So kilograms per cubic meters or per liter per second. So this is the local production rate by 3 different pathways, heterotrophs and the 2 pathways by the autotrophs. And what you can see is that most of the reactors, dark blue, there is almost no production. But the production of N2O really happens in a very little volume proportionally in your reactor. So the heterotrophs, of course, mainly do it here when there is a feed, when there is high ammonia. And the autotrophs do it mainly because in this case, you have a local recirculation of some oxygen. So these 2 pathways are actually activated here. And then if you would do a scenario, for example, you increase your ammonia, which often happens, you see things shifting, not so much for the heterotrophs, but the impact on the production of the autotrophs, this pattern is now quite different. Why? Because, of course, the ammonia gets deeper into the aerobic zone now. Yeah. So this is just to illustrate that the root causes, let's say Pareto principle kind of applies. Maybe 80% of your N2O emissions are caused by 20% of your reactor volume. And it's all about, yeah, having understanding on these tiny volumes and maybe managing them. So here you can see the same plots, but quantitatively compared how these pathways contribute to the overall N2O emission. So these 3 pathways, and you can see in scenario 1, so the low ammonia scenario, the heterotrophs were doing most of the production, while actually in the second one, it is really the autotrophs. Yeah, that's almost 80%, more than 80%. So now we go to a full-scale plant in Canada. This is a Canadian reactor. Again, we will not go too much into detail because it's quite complex. But what I'm showing here is 6 different scenarios. Yeah. So this is the top view of the real reactor. anoxic zone, anaerobic, anoxic, and then you have an aerated zone with fine bubble diffusion, yeah, some recycles, things like that. The flow goes like this. And here we see the same reactor, and we visualize, in this case, the liquid N2O concentration. So just imagine you would measure somewhere with sensors. This is actually, if you would move your sensor, this is what you would measure in terms of gradients. There's quite some difference across the scenarios. That what you can already observe. The intensity of the local N2O concentration is quite different. For example, if you compare the extreme scenario 3 with the base case scenario, what happened here is they switched on the winter package. This is kind of a swing zone they use to catch ammonia peaks in the winter. It actually leads to a drastic reduction in N2O, but it also leads, of course, to higher nitrates because you lose a bit of your denitrification capacity. So this is quite extreme, as you can see. But if you would measure with sensors, it would be quite tricky, the image you would get here. Another important thing is if you look at scenario 5, in this case, I think it's a winter scenario combined with an elevated sludge concentration and a somewhat lower aeration. You can see that suddenly you get also a liquid N2O production at the effluent here suddenly, which is not the case in the other scenarios. Yeah, so this is what you can nicely visualize. If you look at the gas, this is the same scenarios, but for the gas. So this is really the stripping at the surface of the reactor. So now if you would measure with a hood, this is what you would measure. And again, the patterns are quite different if you compare these different scenarios. So of course, if you're a wastewater practitioner, everybody understands there are huge dynamics, and also so these intensities or these zones literally shift across the reactor as function of how the year progresses, how your operation is done. Just to quantitatively come back to these two scenarios, these extremes, so the one with the swing zone on and the one without the swing zone on, it led to a 50% reduction of emissions almost, and well, 46, let's say, of the emissions in the gas phase, and then 50% of the production reduction. Yeah, we kind of distinguish because you can also lose some N2O in the effluent. That's what you can see here. This reduction was also significant. Yeah, 50% or so. So in the end, the net balance, yeah, of your N2O is some goes to the gas, gets stripped, some goes to your effluent sometimes. Yeah, which is not often taken into account. So now we are also with this customer guiding him with the measurement campaigns because they are planning a lot of measurements. And then we use such simulations to guide a bit. If you would do liquid sensoring, where would you put them to get the most accurate view of your emissions? Because you don't want overestimation, but also you don't want underestimation. And the same for the gas hoods, depending a bit on how many hoods they would use, 1 or 2, or 1, 2, 3 sensors. This is how we now help guiding a bit the measurement campaigns. So this brings us to the conclusions of this slideshow. So we believe that the Pareto principle kind of applies to N2O. 80% of your N2O might be produced in only 20% of, or even less of your bioreactor volume. So it's about understanding the production volumes. And we believe also that N2O measurements reveal symptoms. So they really give you an idea on how bad it can be or what can be the variation. And then, but really to cure the patient, we believe you really need to address the root causes. And to stay in the healthcare jargon, our solution acts kind of like an X-ray. So you have kind of a 3D diagnosis of reactor. But of course, it's more than X-ray because with the what-if testing of these models, you can then virtually test mitigation strategies. So we currently have customers that are now going to try to use the models for regulatory reporting even, and try to limit the measurements as much as possible because the models allow testing flexibility. Okay, that was my presentation. Thanks a lot for your attention.
Thanks, Wim. Thanks for the nice presentation to show us how to use CFD combined with kinetic models to do X-ray about the N2O generation.